Epsilon n theorem is the main theorem for VC dimension theory. Let XH be a set system and D a probability distribution over X. X is input domain. H is the set of hypotheses we are considering. And let n be an integer satisfying which is greater than 8 over epsilon and 4 over epsilon times log theta function to n plus log 2 over delta. From the inequality on this is less than or equal to n to the d if d is the VC dimension, right? So when n is greater than or equal to 4 over epsilon times d log 2n plus log 2 over delta, this is also okay. So when n satisfy, which is greater than 8 over epsilon and 4 over epsilon times d log 2n plus log 2 over delta, then let S consist of n points drawn from distribution D, so which is randomly drawn from a given distribution D, with probability greater than 1 minus delta. Every set in hypothesis set H of probability mass greater than epsilon intersect S. Okay, which means so if the set in hypothesis class H having mass less than epsilon, at every samples with probability 1 minus epsilon for any given H that satisfying the probability X belong to H is less than or equal to epsilon, satisfy the sample is not inside the hypothesis H. Okay, so when you collect n data point with probability 1 minus epsilon to the n, any sample in our set S does not belong to the given hypothesis H that has this property. Okay, so when we study pack learning week 3, for the analysis we just find the upper bound of the event. The hypotheses have mass less than epsilon, and every sample in a set S does not belong to the hypothesis H, which is upper bounded by 1 minus epsilon power to n, right? And also, we can upper bound the number of hypotheses by the total set of hypotheses the cardinality of hypothesis set. So from this, we can find the sample complexity of finite size of hypothesis set, which was pack learning we have discussed on week 3. So again, we have this probability for any given hypothesis H that having this probability, then with probability at most 1 minus epsilon power to n, all elements in the randomly generated set S do not belong to the hypothesis H. Now we have to find the cardinality of hypothesis H, but the problem here is we are considering infinite hypothesis class. So we cannot multiply the cardinality of hypothesis set H to here. Okay, previously we just simply multiply the cardinality of H and we just find the size n that satisfy this. But here H could be infinity, right? And with infinity, we need infinite number of samples to guarantee this inequality. That's why we have to introduce VC dimension to understand the behavior of infinitely many hypotheses in our class. Okay. So for the proof, we will use an interesting proof idea, which is double sampling technique. Okay, before explaining what is the double sampling technique, I want to explain why we have to use such additional technique. Why not simply use size n dataset directly? Okay, so in the previous peg learning case with hypothesis, with finite hypothesis class, essentially at the time we consider for a given hypothesis, consider the probability for the event that when we randomly generate n data point, what is the probability every samples are outside of our hypothesis or outside of error case. Okay, since we consider for given hypothesis, every samples is IID random variable with parameter epsilon. Okay, so every instance independent and with probability 1 minus epsilon, the sample is outside of error or outside of hypothesis in our case, and everything is independent. And for the proof, we also consider this tree. For any other hypothesis H, we are considering another random sampling procedure. Okay, so basically, we use union bound, and then we calculate the probability for a given hypothesis H that does not include any error case or any sample belong to the hypothesis, which is simply upper bounded by 1 minus epsilon to the n, and then take the all hypotheses in our hypothesis class, which just simply multiply the cardinality of hypothesis set. We now first sample n data point and then consider hypothesis so that we can deal with infinite size of hypothesis class. Okay, first sample n data point, and then from the VC dimension theory, we know that there are at most this amount of possible hypotheses. So we can change the problem from infinite hypothesis class to finite hypothesis class. Then now we can think that using this finite hypothesis can be defined on these n data samples. Again, we can use union bound, and again we can use this kind of analysis. We can expect that We just need to find n that satisfy this inequality as before, as we did for Peng learning, for finite hypothesis class. But the problem here is, after we sample data point, this instance, this realization is not random. After we sample, the outcome is not random. So for this number of hypotheses, we cannot define probability. This is either true or not. Okay? After we sample n data point, this is essentially either this hypothesis include any data point or not. Just a fact. So we cannot use this tree, the union bound tree, because each hypothesis test, so whether any data point belong to the hypothesis or not, the probability is not 1 minus epsilon power to n anymore. Okay? I wanna highlight again. After you sample n data point, there's no randomness to check whether any data point belong to the hypothesis class, hypothesis function or not. Okay? So now we have to use double size samples. So instead of just sampling n data point, now we will sample 2 times more, 2 n data samples. Okay? This is the tree. After randomly generate 2 n data point, we will randomly cut half of data. Okay? And then just use the half of data as the true our data set, and the remaining half as the remainder. We don't care. So we just care whether the selected hypothesis includes any of data point of the true data point, and it is absolutely fine whether the other data point in the remainder has some component in the hypothesis. Okay. The randomness comes from the set selection from 2n data point to n data point. Okay, which means first, from 2n data samples, we can restrict the number of hypotheses from infinite hypotheses to pi 2n. Okay, there is a class of hypotheses. Okay, now we have finite hypothesis class. And the second step is, from 2n data point, we will randomly choose n data point. So for this random sampling, we will use union bound. So we will pick one of hypotheses belong to this finite hypothesis class, and then we'll test whether this hypothesis will not include any element from this randomly selected, randomly generated n data point. Okay, there is randomness from 2n data point to n data point random process. So maybe we can find some probability distribution for this. And since we know that there are finite hypotheses, we can use the union bound again, and then we can analyze this theorem. That is double sampling technique. Introduce additional randomness from oversampling and then pruning process. First, randomly pick the 2n data point and then restrict the hypothesis class so that it seems like finite hypothesis class, and then add additional randomness by the pruning process from 2n data point to n random data point. Okay, let's dive into the proof. So let E1 be the event. So remember what is E1. E1 be the event that there exists a hypothesis H such that the distribution D generate a data point inside the hypothesis H. The probability for that event is greater than or equal to epsilon. But for the n sample, there is no such element from the hypothesis H. Okay. So to show this theorem, it suffices to show that the probability of E1 is less than delta. Okay, because the E1 event is the error we want to analyze. The E1 event means there exists a hypothesis that has error probability more than epsilon. But since the samples has zero intersection, so zero error, there is possibility we can think the perfect samples always indicate very nice hypothesis. Okay, so when we choose empirical risk minimum hypothesis, then basically we can immediately find very nice hypothesis of which error rate is less than epsilon. Okay, and let S prime be a set of random samples with size n. So another n random sample, independent random samples, and let E2 event be the event that there exists some hypothesis such that the error rate is greater than epsilon, and number of element in the hypothesis H is equal to 0. So up to now, this is exactly the E1 event, but we have additional condition for the E2 event. For that S prime sample, the n additional random samples, the number of data point in S prime also include member of H is greater than or equal to epsilon times n over 2. Then of course E2 is subset of E1, so E2 event is subset of E1 event because E2 event has one more condition. Okay, so assume that there exists H star such that the probability of H star is greater than or equal to epsilon, and the number of data sample in S the member of S also member of H star is equal to 0, so there is no error. Then if S prime has epsilon n over 2 data point in H star, the probability for that event is greater than or equal to 1 over 2. then probability E2 given E1 is greater than or equal to 1 over 2 since S and S prime are independent. Okay. So this statement is a very trivial. Since S prime is totally independent to S, the condition of E1 essentially doesn't affect the S prime. Okay? And E2 only has one more condition, this. Okay? So when E1 hold, then to make E2 also true, we just need this part. And if the probability of this part is greater than 1 over 2, then we can say the probability E2 given E1 is greater than 1 over 2. Okay. And since S prime is a set of n random samples, the distribution of this is binomial. There are n trial, and the probability is this error probability, PDH star. Right. Let W be a random variable according to binomial distribution like this. And then when this probability parameter is greater than or equal to epsilon, essentially we have this. And from the condition of this theorem, n is strictly greater than 8 over epsilon, and the Chernoff-Pfaff inequality, we have this. Okay, so this just simply use the concentration inequality Chernoff-Pfaff. Okay, so we found this just show that this is true. Okay, so therefore by using the fact that S and S prime are independent for H star such that probability H star is greater than or equal to epsilon, we have this. Okay. So we have this conditional probability, how to use this conditional probability. We will use this to define some upper bound of E2 probability. So since upper bound of E1 probability. So since E2 is equal to the intersection of E2 and E1, because E2 is member of so E2 is subset of E1, so this is true. And from Bayes' rule, we have this, the E2 intersection E1 is equal to probability of E1 times probability E2 given E1. And we know that this one is greater than 1/2. So replace this by 1/2 and having this sign. Right. So essentially the probability of E1 is less than 2 times probability of E2. Okay, so to show probability of E1 is less than delta, we just need to show that probability of E2 less than delta over 2. So here we use doubling technique. We first define E2 prime as the event that there exists hypothesis H such that there is no error event for the n size sample, and there is epsilon n over 2 error event for the another independent n size of data sample S prime. Okay, so let k is equal to epsilon times n over 2 to simply use this by k. Right. And let's define another event, EH. The event EH is this, the number of data points in H from first n data sample is equal to 0. Number of data points in H from S prime is greater than or equal to k, which is essentially the same with this event. And from this event, we can think EH event as like this. We sample 2n instances and then separate them to construct S and S prime so that both S and S prime have n element, and which is referred to as double sampling technique. Okay, then independently to hypothesis H, when the 2 times larger sample size set S and S prime union, when the number of samples belong to H from this union set is greater than and equal to k, what is the property EH holds for the given Sn S prime? From the definition of EH, we can add this condition to here with equal sign. And from this property, so when we have condition, and when we move one of this condition to this side, then we have this inequality. That is very simple trick for multi-conditional event. And then this property comes from the fact that the S prime union, this information is redundant when this information is given to us to define EH, because EH is just simply count the number of data point. So the from S belong to H is equal to 0, and S prime belong to H is greater than or equal to k. When we have this condition, the all other members of S and S prime information just redundant. Right, and since this is given to us from EH condition, we can remove one of the condition, this one. So now we have this, and we can relax the condition. We can restrict the condition to more. So from greater than or equal to k, just make equal to k. Then we have this inequality sign. Okay, so then what is the property of this? From 2n samples, there are k special instance which belong to the hypothesis H. And when you randomly randomly split the 2n data set into n and n data set, what is the property? The randomly selected n data point does not include any special point. So this is exactly this. So the case selecting n from 2n minus k, so excluding all k instance, and then make n subset over all possible cases from 2n, includes all special instance, and choose n instance to randomly generate S subset. So from simple calculation, we have this inequality. So the property EH for any given H is upper bounded by this. And from the fact that our VC dimension, we know that how many different hypotheses can be defined on 2n size data set. Okay, so from that we can find out the probability of E2. So the probability there exists hypothesis H that satisfy all the sample S does not belong to hypothesis H, but the data point S and S prime belong to hypothesis H as much as n is epsilon n over 2. Okay, and then apply union bound, and previous page result we have this, and this one is upper bounded by the Shatter function and VC dimension. Okay, so therefore the probability of E2 prime is upper bounded by this. So to make this one is less than or equal to delta over 2, what is sufficient condition? The sufficient condition on n is this. When n is greater than or equal to 4 over epsilon times this, we can guarantee that probability of E2 is less than or equal to delta over 2. And from this, we can conclude the theorem.